Section 6.5, we're going to talk about conditional probability. Here's an example. Suppose that we toss a single die one time. Here's the sample space, right? Toss a die one time and look at the number on the top face. It could be a 1, 2, 3, 4, 5, or 6. And maybe what we want to know is what is the probability of getting a 1? Well, if we don't know any other information, we would say that that's 1 out of 6 because that sample space is equally likely. But now, let's find this. What is the probability of getting a 1? Now, I'm going to write this. That vertical line, I'm just going to say is the word given. What's the probability of getting a 1 given, so I'm going to ask you now, what's the probability of getting a 1 given that we know we got an odd number? So the first case was if you don't know anything, just what's the probability of getting a 1? You would say 1 out of 6. But now if I ask you what's the probability of getting a 1, but I give you some additional information. I tell you that I'm telling you that we got an odd number. So what is the probability of getting a 1 now? So the probability of 1 now depends on some other information. So it changes the sample space, right? The sample space is no longer 1, 2, 3, 4, 5, 6. You know that you got an odd number. So the new sample space is really just 1, 2, and 3. And now the probability of getting a 1, given that you got an odd number already, is 1 out of 3. So I'm going to write a formula up here on the top right. What is the probability that the event E occurs given that the probability F has already occurred? So in our example, E might be the probability of getting a 1, and F might be the thing that's already occurred, which is getting an odd number. So the formula goes like this. It's just a fraction. The top is the probability that both of them occur. You have to get E and F, and the denominator is just the probability of F. So the way I remember this is that I want the probability that E occurs given that F occurs. I intersect them on the top, and the bottom, the denominator, is just this one right here. So let's do this. Let's multiply both sides by this denominator. Multiply each side by the probability of F. So I'm going to put that probability of F up here, and when I multiply it over here, it's going to cancel. So I'm going to write this. I'm going to say then that the probability of E and F is equal to the probability of F times the probability of E given that F has already occurred. So this formula tells us that if we want the probability that two events occur, this one and this one, like this first one and the second one, it's going to be, here's how we're going to get it. We're going to take the probability of one of them times the probability of the other, given that the first one already occurred. Here's an example. Suppose that at some school, there's an equal number of female and male students, and that 5% of the male population is colorblind, right? So we know that at this school, same number of male and female, and 5% of the males are colorblind. What we want to do is find the probability that a randomly selected student is a colorblind male. The way I'm saying it is this: we want this, the probability of being colorblind and male. Now I see this and, it's an and these two events I think are dependent, right? They're dependent. These are dependent because the probability of being colorblindness depends on whether you're male or female. So we have a formula for this. The probability of C and M is, okay, we could say the probability of male times the probability of being colorblind given that you're male. Let's just take a quick look and see how we match the formula. I'm up here. So E intersect F. We have C intersect M. It's the probability of, now it doesn't matter if it's the first or second, but I'm writing it here where it's the second. So the probability of the second, now that's probability of male, and then times the probability of the first one given that the second one occurred. Probability of the first given that the second. If I just kind of match this up, it's going to look like this. The probability of E intersect F is equal to the probability of F times the probability of E given F. All right, so I'm just trying to make these things match, just with different letters. So let's see what we're going to get here. The probability of being colorblind and male is the probability of being male. Now, this is going to be 0.5, right, because it's equally distributed between, the population is equally distributed between male and female, so half male, half female. And the probability of being colorblind and male, okay, well, that's 0.05, right? 5% of males, given you're male, 5% chance you're colorblind. Multiply those together, and we get 0.025. So what it says is that the probability of just randomly selecting some student out of this population, that student is colorblind and male, is 0.025, or if you like, you can say that there's, I'm going to move this over, a 2.5% chance that that's actually going to happen. Let's take this just a little bit further and say this. The probability of E and F is equal to, okay, it's the probability of F times the probability of E, given that F has already occurred. Now, if, let's say this, if E and F are independent, all right, that means, all right, they're independent, which means independent. They're independent, which means that E and F have really nothing to do with each other. If E occurs, it has no effect on F occurring. If F occurs, it has no effect on E occurring. So what that means is that this part right here, the probability that E occurs, given that F occurs, because they're independent, just reduces to the probability that E occurs. Does that make sense? E and F have nothing to do with each other. So if F occurs, it doesn't matter. That has no effect on E. So the probability that E occurs, given that F has occurred, that's the same as the probability that E occurs. So then we get this formula right here. The formula becomes the probability that of E and F both occurring becomes the probability of F times the probability of E, but I'm going to rewrite that. And I'm going to say that the probability of E and F is equal to the probability of E times the probability of F. And this is going to be true if these two events are independent. So how do I know? I'd have to be told that the events are actually independent. Then, if they are, I could just use this multiplication formula.